Hi, my name is Ray Deyoe, and I'm presenting a case study on a large-scale industrial cogeneration project called Port Arthur Steam Energy LP. So some quick facts about PACE at a glance. This is a project that's located in Southeast Texas, down in Port Arthur. And it was a joint effort between a petroleum coke calcining company called Great Lakes Carbon. It's now a different entity, but at the time it was Great Lakes Carbon, Valero Refining, Entergy Gulf States, which is the Entergy affiliate in the eastern part of Texas there, and my company, Integral Power, who was the developer and asset manager for these years of operation. So this project takes very high temperature exhaust heat from a petroleum coke calcining operation and converts it into high pressure process steam and some electricity. It has the capability of exporting about 450,000 pounds per hour of net process steam to the neighboring refinery, as well as producing 5 megawatts of power at the same time. Originally, this project, I should say, was built back in the early 80s by Dynegy's predecessor company. We took it over and acquired it in 2004 and rebuilt and upgraded the facility to what is today called Port Arthur Steam Energy LP. In terms of a general equipment configuration, you can see here that this project has three waste heat recovery boilers that are connected to three petroleum coke calcining processes. The boilers actually connect to what the calciner calls a pyroscrubber, which is a very large refractory lined box, if you will, that allows the calcining exhaust to have residence time and be able to and have unburned carbon particulate have a chance to find oxygen and continue to burn. So as you can imagine, there's a very high temperature that comes off of that process. And if PACE were not present, then those gases would otherwise go to the sky, go to the atmosphere out of kiln stacks at approximately 2,000 degrees. But PACE is there, and so through a series of isolation dampers, the gas is instead directed through our boiler systems, and we produce high pressure steam, most of which goes to the neighboring refinery, a little bit of which goes into a back pressure steam turbine, which lets down some steam to serve deaeration. And so that little bit of steam that's dropped to the deaerator is sufficient to produce anywhere from 4, 5, 6 megawatts, depending on how much process steam is going to the refinery at the time. The project also has a large demineralizer system on site. We actually take clarified water back from the refinery along the same pipe rack as the steam line. We take their clarified water, we demineralize it on our side of the fence to produce our own boiler feed water. So the refinery gets the benefit not only of the steam that comes to them with no associated emissions, but also they get the benefit of some demineralizer capacity as well. Getting down into the weeds a little further on major equipment, you'll see each of these three boilers has not only interconnection facilities and dampers, but they also each have a magnesium hydroxide injection system. We'll get into that in a little bit. They also each have a multi-clone system on the tail end, which is there to remove even more particulate that's left over in the process. And then each boiler is followed by an induced draft fan, which is there to overcome the pressure drop of the gases through the boiler and help pull those gases through the boiler and up and out of a boiler stack. And then each boiler also has an acoustic soot blowing system as well. The back pressure steam turbine generator that we have is a GE unit, 6.5 megawatt. I mentioned the demineralizer system. It's about 1,000 GPM worth of demin capacity. And then we have enough demin water storage on site such that if we were to lose clarified water flow, we could still run the project for many hours. I think we have something like 15 hours worth of demin water storage on site to be able to run the project. The project also includes a 2.5 mile steam pipeline that connects the host plant and our facility to the neighboring Valero refinery across quite a bit of swampland. So it was quite a project building that pipeline in the old days. I've included this process flow diagram. I know it's very difficult to read here, but I've included it in case there's some interest if someone wants to go back and look at just exactly how all this is arranged from a process flow perspective, you could go back in the presentation and look it over. Some equipment highlights, just so you can get a feel for what these things look like and how big they are. You see down in the bottom right corner there, that's our little 6.5 megawatt back pressure steam turbine generator, which effectively acts as an efficiency valve, if you will, to let some steam down to serve deaeration. You see on the top left there, that's one of the multi-clone systems, followed by the induced draft fan that's on the tail end of one of the three boiler systems. You see there in the middle, that is one of the boilers. It looks rusty here, but that's because when you have 2,000 degree gases going through a boiler, it's very hard to keep paint on anything. So they essentially design these things with skin that gets a little bit of a light rust on it, and then that's the way you leave it. Bottom left, this project has its own, of course, distributed control system. In our case, it's an Emerson Delta V system. Top right, you see that's our admin building, which houses not only offices and all that, but also has all the electrical systems, MCC room, all of that is there. The steam turbine generator and boiler feed water system and all of that is in that building. And you see just to the top right of that building, you see that's our deaerator, which has the water that drops down into those boiler feed water pumps that are in the building. There's three unique challenges and solutions with this project that I wanted to point out. First of all, there's each upstream kiln system for the calciner needed to be able to operate while its respective boiler is down. And at the same time, if you want to be able to work on a boiler that's down while the calciner is up, then you have to, of course, have double isolation so that you can have personnel inside that system. So that presented some unique challenges. That's overcome by a system of diverter dampers. You see there on the bottom right picture there, you see those counterweights that are there at the ground. Those are vertical dampers that are in that square duct there that are actuated hydraulically with those counterweights. And if both of those dampers are down, then that provides double isolation to be able to isolate the boiler and have personnel inside the boiler if that calciner that's off to the right is still operating. One thing that's very unique, you see that picture there on the left, one of the particular kiln stacks at this location there wasn't room in the duct between the boiler and that hot stack to put a damper. And so instead we put what we call a stack cap on this kiln stack. And you see there, those are kind of pie-shaped damper system that has counterweights on them. That damper is held closed by hydraulics. But if there's some kind of a trip in the boiler system and those gases need to go back to the kiln stack, then those counterweights will pull those pieces of pie open and those 2,000 degree gases will go back out of that hot stack. But when the boiler system is running on that particular kiln, then those pieces of pie are closed, and there's a cap essentially on top of that kiln stack so that all the gases can go through the boiler system. Next, in terms of petroleum coke calcining, that exhaust has sulfur in it, has SO2 and SO3, which of course leads to sulfur dew point corrosion considerations on the boiler surfaces, both in the cold end of the boiler as well as during startup conditions when everything's cool. A couple of ways that we've overcome that. One is that we run our deaerator at about 60 pounds. That keeps the boiler feed water temperature up high enough that we keep the tube surfaces inside and out in the boiler economizer, such that we try to avoid that the sulfur dew point. In general, we try to keep our stack temperature at 400 degrees or maybe even slightly higher to make darn sure we stay well above the sulfur dew point, and not only in the back end of the boiler, but also through the multi-clone, the induced draft fan, the stack, all of that, which is all carbon steel material. We've got to avoid the sulfur dew point. The other thing, and this is what's pictured here, that we do that's unique is we inject a 60%, roughly 60% slurry of magnesium hydroxide upstream of each boiler. You see there the location where we inject it on in the ductwork just ahead of the radiant section of the boiler. We do this at each of the three boilers. That magnesium hydroxide reacts and neutralizes with the SO3 in the flue gas and effectively lowers the acid gas dew point, and really helps to protect the cold end equipment. We've really seen a lot of success with this over the years. We make sure we inject enough to coat the tube surfaces and really do a lot of neutralization, so that when we do a startup, we've got plenty of mag hydroxide on all the tube surfaces. But this has been a great system for us. Lastly, another thing that's unique about petroleum coke calcining exhaust is that it has entrained particulate in it. There's just some unburned carbon and other particulate that is entrained in the gases and ends up into the boiler system. If you don't do anything about it, then it ends up coating on the tube surfaces. Ultimately, it will start to bridge, and that causes, of course, pressure drop through the system on the flue gas side. It also causes a loss of heat transfer, and that's not good for anybody. So we don't want that induced gas fan to have to work any harder than it has to, and we certainly want to make as much steam as we can. And so the original project, built in the early 80s, had a steam soot blowing system. We didn't like that because ultimately there was problems with it. The guys didn't like to maintain it, and of course it wasted steam. You know, this is steam that we could otherwise sell or go to produce electricity with. And so in 2005 we converted over to an acoustic soot blowing horn system. So each boiler has an acoustics horn just downstream of the economizer, and that horn is tuned to frequencies that can affect all the upstream tube surfaces. And ultimately, we've had a lot of success with this. It basically is like a giant foghorn going off in the duct, and you feel a little rumble, but it vibrates those tubes and knocks the particulate off of the tubes. Why did we do all this? You know, this is a tough application, a lot of expensive gear to go out and get this heat. Why do we do it? We do it because it's environmentally the right thing to do. Certainly, it improves energy efficiency and has its own share of economics, and it's a poster child for reducing carbon footprint. But there's a couple of other things. One is that that little 6.5 megawatt steam turbine that we have is capable of running both our plant and the host plant in what we call island mode, where if the incoming utility power from Entergy is interrupted, then we can essentially function as an island and run our plants. And that little feature has saved our host plant from going dark probably at least 10 times over the course of the last 15 years, and has really been a value add. The other thing is that when this project is operating at capacity, certainly there's money to be saved by capturing this energy and producing steam and power with it. You see that there, but also because we're avoiding the burning of about 3.6 trillion BTUs per year of natural gas that would otherwise have to go to produce this much steam and power. The beauty of that is that we're reducing CO2 emissions by an EPA estimated 159,000 tons per year, or the equivalent of about 27,000 cars off the road. So we were successful in getting an EPA award back in 2010. We're very proud of that, and we're very proud of what this project can do. I wanted to mention lessons that can be learned from our project here at Port Arthur Steam. Certainly could and we believe should be applied to recovering waste heat from some of the other tough applications out there. Like, certainly there's more calciners in the country that don't have waste heat recovery, but there's cement plants and lime plants and carbon black, steel manufacturers, waste incineration. These are all very high temperature processes that have a lot of byproduct waste heat, but also have a lot of particulate, abrasion, corrosive products in the gases, and they're tough. Those are tough applications, but I think we've proven with our Port Arthur Steam Energy Project that those things can be overcome and that there can be real success here. There was a market survey done by ICF back in 2015. You see that on the bottom right on this particular slide, and if you just look at the amount of megawatts that they went out and researched could be recovered from industry over that had byproduct heat over, say, 450 degrees Fahrenheit, it's over 9,000 megawatts if it were all converted into power. So there's certainly a big demand here for projects We're excited about that, and we hope that this Port Arthur Steam Energy project, this case study, can be a bit of a poster child for other industries to look hard at actually doing this. I want to thank you for your time today. Certainly, if you have any questions, feel free to reach out to me either by phone, by email, whatever works. I'm here, would love to chat, and would love to collaborate on a project. Thank you so much for your time.